Good afternoon, everybody. Welcome to today's NCCAV seminars. As you may know, the last Friday of each month, we're going to be having a CCAV seminars. The previous seminars have been already uploaded to the NCCAV websites, and you can take a look if you have been missing any of those past exciting seminars. I would like to take this opportunity to thank the sponsors of the project, NCDOT, as well as other gold sponsors of the project, Downtown Greensboro, Verizon, and RTI. And for today's presentation, we are excited to have Dr. Habib as a speaker for today. The title of today's talk is Mobile Mapping Systems for Accurate Documentation of Transportation Corridors. Dr. Habib is the Thomas Page Professor of Civil Engineering at Purdue University and the co-director of the Civil Engineering Center for Applications of UAVs for Sustainable Environments. He's also the Associate Director of Purdue University's Joint Transportation Research Program. Dr. Habib's research interests span the field of the satellite and aerial mobile mapping systems. He has been focusing on modeling and on modeling perspective geometry of non-traditional image scanners, automatic matching, change detection, automatic calibration of low-cost digital cameras, object recognition in imagery and point cloud data, LiDAR mapping, and integrating photogrammetric data with other sensors datasets such as GNSS, INSS, GIS dataset, multi and hyperspectral sensors, and LiDAR. Over the last 6 years, he has been involved in the development, integration, and utilization of wheel-based and UAV-based model mapping systems for a wide range of applications in precision agriculture, geometric documentation of transportation corridors, archaeological documentation, crisis reconstruction, and infrastructure monitoring. I also would like to thank Dr. Hashemi for getting us in touch with Dr. Habib. It's really a pleasure to have you, Dr. Habib, today. And without any further ado, I would like to invite you if you could start the talk today. Thank you so much.
Thank you very much for the introduction and also for the invitation to share some of our recent work with everyone who's listening. So I would like to start by sharing my screen. Hopefully everyone can see my screen.
Yes, we do.
Okay.
I think it is in the speaker mode. If you can switch the.
Oh, yeah. So it's not clear to me which one. Okay. So hopefully now it's correct.
Not yet.
You don't see the current one, the correct one yet?
Not.
Still in the speaker mode, presenter mode?
Yes.
Okay, let me swap again. Do you see the full slide now?
No, it still is the same, no change.
That's a bit strange. So let me even duplicate. Does it?
Yep. Perfect.
Yeah, duplicate mode. Okay. Okay, so thank you very much again, everyone, for joining this talk. And today I'll be talking about geometric documentation of transportation corridors. And just to give you an idea about my background, I am coming from geomatics engineering. And today I will be talking about this mainly from the perspective of geomatics engineering. So I'll start by explaining what is geomatics engineering. It has been traditionally defined as the science for the collection, analysis, and interpretation of data, which is mainly related to the Earth's surface. And if you look into the geomatics engineering life or data cycle, we start usually with the data acquisition. You have a wide range of data acquisition modalities and platforms. Then we proceed to the data modeling, where we try to relate the sensor observations to the phenomena in the object space we are observing. Finally, the data analysis, where we are talking about how we can relate those observations and the model data to important aspects we are looking in the data. And finally, feeding this information to decision-making process. So in my area of work, I'm mainly focusing on the first three aspects of the geomatics engineering data lifecycle, which is the acquisition systems, the data modeling, and the data analysis. So if you look into the geomatics engineering, we have lots of applications where traditional as well as emerging applications. So just to give you an example, we are right now applying technology for infrastructure monitoring, digital agriculture or precision agriculture, energy sector, and transportation management, which is the focus of my talk today. So if we look why we are able to address these wide range of applications, it's just because of the new developments in the technology in terms of sensors, platforms, and this is really the main motivation or the cause for giving us the tools to address the needs of these non-traditional applications. So one of these developments, I would say what we call mobile mapping systems. So the traditional definition of mobile mapping systems, we can say that these are systems or platforms that are equipped with a group of sensors or measurement systems which are integrated together to provide information about the three-dimensional trajectory of the system, as well as the objects which can be seen or perceived in the field of view of the sensors on board, whether they are cameras, whether they are LiDAR systems, or even radar systems. So just to give you an idea about what kind of mobile systems we have, so we have the traditional ones, which are basically mapping platform either on space or manned aircraft. And then we have the terrestrial or wheel-based mobile mapping systems. These are examples here, one for transportation corridors mapping, and the other one here is for agricultural mapping. We have the unmanned airborne vehicles, unmanned ground vehicles, or even portable systems, like whether they are backpack or even mounted on a tripod. So today I will be talking about these systems which are in red, and those are systems we developed here at Purdue University within my research group. So why we are really believe that, or why mobile mapping systems are useful for transportation? Because they can be used for a wide range of applications related to transportation corridor mapping and transportation management in general, whether it's lane width estimation, that's very important for construction work zones, pothole mapping or anomaly detection along the pavement of the road, mapping roadside ditches, infrastructure monitoring along the road transportation corridors, whether they are bridges or mechanically stabilized earth walls, documentation of crash scenes, support of winter operations, for example, by evaluating the volume of salt in salt storage facilities, and the lane marking reflectivity analysis. And I would say that all these different applications are very important for, I would say, the ultimate goal, which is developing or producing high definition maps for safe autonomy. So that's what we can really see as the ultimate goal of our research work, which is using mobile mapping systems for the management of transportation corridors. And just before I get into the presentation, please feel free to ask any questions anytime during the talk here. So this is our focus when we look into like mobile mapping systems or remote sensing technologies in general for geometric documentation of transportation corridors. we have to look into these 5 aspects, and one of them is the sensors and the platforms which we will be using to deploy these sensors. So these are just some examples of mobile mapping systems for mapping of the transportation corridor. In terms of geomatics engineering, we are mainly quite interested in deriving very precise geometric information about the object space. So the system calibration process is quite important. And then once we have the data, we have to do some data processing. And here I'm talking about 2 types of data processing. So general data processing, these where we take the geospatial data collected by the sensors and the platforms on top of our mobile mapping systems. And here we're talking about like regular or more or less a common data processing applications, for example, ground filtering, segmentation, classification of objects, normalization of lane marking intensity or intensity data in general, detection of lane marking, and solving some problems whenever we have absence or navigation issues, like when we drive under heavy canopy, for example, or wherever we have GPS signal loss under bridges. And then we have these application-dependent data processing. And if you remember, we said that the whole idea of having this geospatial data for geomatics is that we have to provide this data and the information we have to the end user. So the visualization of our derived or products to the decision maker in a way that it's easy for the decision maker to query or look at the data. That's very, very important. And it's one of the aspects that we have been focusing on. So in the talk, I will try to say briefly, mention some of the things we have been doing in each one of these aspects. So let me start with the sensors and the platforms and the system integration. So like my main message here, which I would like to convey, is that we are lucky right now at this time. We have lots of sensors. We have LiDAR units, which are very cost effective. We have digital cameras. We have navigation units, which can be either global navigation satellite systems or inertial navigation systems. And this is an example of one of our systems. We call it Purdue wheel-based mobile mapping system, high accuracy. And this is designed to derive accuracy of in the range of 1 to 2 inch for mapped objects along the transportation corridor. That's another system. We call this one here ultra high accuracy, where we have higher end LiDAR units, higher end navigation units, and here we are trying to derive geospatial data at the sub-inch level of accuracy. For some of the applications where we have limited access to the areas we map, we developed unmanned ground vehicles, which are equipped with cameras, with LiDAR and navigation units. For some applications, we might need even more portable system that is not only deployed along the highway. So we have this backpack mobile mapping system. Again, it's equipped with a LiDAR, navigation unit, and camera. This is like an image of this system here while we are doing monitoring of the shoreline to determine the erosion along the shoreline in South Lake Michigan. We can even take this unit here, we can mount it on a car. We have this what we call mobile bag, that much low cost or cost effective system, and that can be used for lots of mapping applications. For the stockpile volume estimation, we developed this platform. We call it SMART, which stands for Stockpile Monitoring and Reporting Technology. And it's really designed to give DOTs the option or the ability to evaluate the volume of the salt in their storage facilities for the support of winter operations. In addition to all these systems, which are, I would say, terrestrial systems, we have now an access to lots of unmanned aerial vehicles. So you can either have off-the-shelf aerial vehicles that you can buy these units anywhere from $1,000 to $2,000 or $3,000, which have very good camera systems. They have also GPS that performs geotagging of the acquired imagery. You can have these customized unmanned airborne vehicles, and these are some of the systems we developed here, where we have navigation unit integrated with LiDAR and camera. This is another unit where we, in addition to integrating the navigation with LiDAR and camera, we have also hyperspectral sensors, and we even have like higher accuracy LiDAR unit integrated with navigation and cameras. So you have all this access to these sensors. Again, here we are looking at the cameras. You have some cameras from 20 all the way to 60 megapixel cameras at a very affordable price. We can say that within $2,000 or $3,000, you can have very good access to these data sets or these units. These are other more systems here. This is a system here, which is a hyperspectral sensor, which takes the band from 0.4 to 1 micron wavelengths, and it divided into 270 bands for agriculture and for infrastructure management. The hyperspectral sensors are quite valuable. LiDAR sensors, again, you have sensors here that range in price from $3,000 to slightly more than $100,000. That's, again, this is unprecedented to have this wide range of sensors available, with some of them being quite affordable. These, and also we have these navigation units that are providing us with the position and the orientation of the platform. You have some units here which are only GPS that cost like a couple of $100. You have other units that cost maybe within $10,000, and units as expensive as $70,000 or $80,000. So for lots of applications, you have this wide range of sensors with different capabilities that you can use for your systems, and you can mount them on airborne or ground systems, or you can have even portable systems. So in order to take advantage of these different modalities, you have to do what we call geometric system calibration. And the whole idea of the geometric system calibration is that we would like to increase the accuracy and improve the quality of the data we derive. So for example, if we derive point clouds from LiDAR and image data, I would like to make sure that these have the highest precision possible. So the way we do this is that we first start by calibrating the individual sensors, whether they are cameras or LiDAR. We are trying to estimate the intrinsic parameters, whether, for example, for a camera, we are trying to estimate the focal length, the distortion parameters that are present within the sensor. And also we have the navigation unit, that's the GPS INS unit. So after GPS INS integration, you get the position and orientation of this point here on the platform. But eventually, we are interested in positioning the camera. So we have to evaluate these spatial and rotational offset between the coordinate system of the navigation unit and the coordinate system of the camera. The same thing, you have a LiDAR unit that has its own coordinate systems. So we are really interested in determining these spatial and rotational offsets between these two coordinate systems. So this is actually the main reason for having geospatial product of high quality, is because of the quality of the GPS INS trajectory, as well as these lever arms and bore side between the different coordinate systems. So there are standard approaches for doing camera calibration. So for example, you have a test field with targets, you take some images, overlapping images, and you have a bundle adjustment procedure to derive the internal characteristics of the camera, as we can see here. For LiDAR calibration, the whole idea there that if you actually have a LiDAR and you do one track, you will get a version of the object space. So that's, for example, point cloud, which is reconstructed from track 1. And then you have another track, you have another version of the object space. And then if basically you have some problems with the relative positioning and orientation of the LiDAR unit relative to the navigation unit, when you look at these data coming from different tracks, it will not align well. So the first objective of the calibration is to make sure that we precisely estimate these lever arms and bore sight to ensure that the point clouds coming from different sensors or different tracks or different systems align well. And if you happen to have a control surface or a control point, you also refine the parameters to make sure that your LiDAR point cloud coincide with the control surface. So just to give you an idea, this is a visual illustration. If you have two tracks of the same LiDAR sensor and you have some problems in your calibration, you can see here that the two tracks will not be aligned well. These offsets here could be in the range of few meters, depending on how far you are from the true mounting parameters. And if you have control, you can see actually none of these point clouds is aligned with the control. So what we do actually is that we establish these calibration procedures to make sure that the derived point clouds from the different tracks are aligned well together with the control points as well.
Professor Habib.
Sure, go ahead, please.
You do these things online in the field, or you do these offline, this calibration?
This calibration is done post-processing, but we do it only once for the system. So once you have the system integrated, and that's one of the things that's very important, that when we build the system here, we have this solid rig and all these sensors are not moving relative to each other. So once we do the data calibration or the system calibration, you don't need to repeat it as long as you believe that your systems are still in the same place. So that's basically what we are doing here. We build a rigid platform, and then once you do the calibration, you don't need to worry about it for every mission.
So do you mean that?
Sorry, go ahead, please.
Yeah, do you mean that you do this after taking the data or prior taking the data?
We do this we collect the data for the calibration. So you can see here, we collect this data. We have a draw, the roadway and the buildings. So we have basically we drive the system with multiple tracks in our facility where we store the systems. We use this data to do the calibration. And after that, you go as a system and collect any data. You don't need to worry about the calibration. And this is something that sometimes happened actually when we work with our UEVs. So when we have the UEV system and sometimes we have to ship the system. So sometime during the shipping, some of these calibration parameters will be disturbed because of, poor handling of the system. So what we have actually is that we have a calibration pattern. We acquire the data in the actual mission, but we follow certain configuration, and we can use this one here to refine the calibration parameters. Hopefully I addressed your question.
Yeah, thank you.
Yes. So yes, so as long as you have within your data this information that allow us to see this discrepancy, we can calibrate the system. But once you calibrated the system and you believe that the units are fixed relative to each other, you don't need to worry about that. So we do something similar, but again, we can include also on top of the LiDAR the imagery data. So again, you have point clouds coming from the LiDAR from different tracks. You have point clouds coming from the imagery. Again, if you don't have a proper calibration, all these data sets will not be aligned well. So we use this observed discrepancy to refine the mounting parameters. And then basically we make sure that all these versions of the point clouds align well. And again, if you have a control surface, you make sure that it fits with the control surface. So we have this, what we call multi-sensor, multi-platform system calibration, where we can simultaneously calibrate the image and the LiDAR units. So basically, whenever we have feature in the imagery, we can find where it is in the LiDAR and vice versa as well. So the way we do that is that we identify common features. Like, for example, we have here reflective targets that can be observed in the LiDAR and the imagery. We have linear features that can be observed in the LiDAR data and in the imagery. And we use those features to do this system calibration. And we have well-defined quality control procedure where we look into the alignment of the point clouds. For example, here the red These are point clouds coming from the imagery, and the blue is the point cloud coming from the LiDAR. So here we are showing actually that the point clouds coming from these two different modalities are aligned well, and we can see this even in 2D. We can take the LiDAR data and the object points, we back project them to the imagery to make sure that this data is aligned well. So this is an example of a calibration test field that basically we move forward and backward, and we use this data to establish the calibration process. So this is just, if you are interested in more details about this stuff, this is some of our papers in this area here. The second part here, or the third part, is the general data processing. And I will just very briefly talk about some of the data processing activities. So one of the common activities is ground filtering, just getting the surface of the Earth and digital terrain model generation. Lots of approaches are there. There are some issues that most of the approaches are mainly designed for airborne LiDAR data where you are looking down. When you have terrestrial LiDAR data, you have very disparate variation or large variation in the point density, and you have also object points of different sizes. So one of the things we have been focusing here is how we can derive filtering techniques that can target terrestrial data where we have a wide range of point density as well as object size. So we started by using some of the existing techniques, and this one here is called cloth simulation method, which is a very nice method actually. And the way it works is quite simple. So just you imagine here that this is a point cloud. So the cloth simulation works by, first you invert the point cloud upside down, and then you have a cloth, and this cloth is defined by some nodes, and we have sort of strings or springs connecting them, and then you can actually control the rigidity of these springs connecting these links. And then you let the cloth drop under the weight of gravity, and then we say that the resting shape of the cloth, that's our digital terrain model, and a buffer around this resting, that's the bare earth point cloud. So this approach is being available for the community since 2016, and I will show you some results. And this is one of the things here. So this is a transportation corridor we have here. We are driving along this here. So this is colored by intensity, and you can see because of occlusions we have lots of gaps in this area here and this area here. So if you use the traditional cloth simulation method, you can see that's basically the derived digital terrain model. And if we cut a profile, you can see actually here that in areas where you have gaps in the data, you have artifacts in the data. So we know actually that this is the ground, this is the ground. So there is no way that the ground in between is behaving like that. But this is the artifact caused by the cloth simulation because of the presence of this large gap. So what we did actually is that we took this initial version and we manipulated the rigidity of the lengths connecting the nodes among the point clouds, and then we did another iteration of this cloth simulation while controlling the length. So you can see this is basically the derived digital terrain model, and if you can see here, we nicely actually follow the terrain here. So just to give you an idea about the differences, you can see here, this is using the original cross simulation. You have these huge artifacts where you have less point density or sparse data, but by modifying the rigidity to be commensurate with this density, with the sparsity, you get more reasonable digital terrain model. So just to give you an idea, this is some of the data sets we have been collected along one of the transportation corridors here, State Road 25. And hopefully the video is streaming is coming smooth. So on top here, we can see the LiDAR data colored by height. Blue is low. As we get higher, we have red. And this is the LiDAR data colored by intensity. So what you see on top is the point cloud data, the full point cloud data, and below here only the bare earth point cloud data. So you can see here we have, that's basically the key problem. Along the road, you have huge or large point density. We have thousands or 20,000 points per square meter. But as you move away from the road surface, you have more sparse data set. So if you use most of traditional ground filtering techniques would have problems in those areas. And by using this adaptive or modifying the rigidity of the cloth, you can avoid those problems here. So I'll just give you a few seconds to look at the full point cloud, color by intensity and height, and this is the Bird Earth point cloud. And while we are looking at this stuff to see the I would say the performance of the ground filtering, I would like you also to see the richness of the information we collect from LiDAR data along a transportation corridor. So here, this is data is coming while driving roughly 30 to 40 miles per hour. You see we have very large level of detail that we capture in this area. I'll just give you a few seconds. You can see here we have some individuals are wearing these retroreflective jackets. These are cones with reflective tapes. So you can see that you can nicely see like the individuals. So here that just gives you an idea about the level of detail in the data. And you can see it's nicely filtered from the point cloud data.
Professor Habib, what are the differences between the two?
These two, you mean?
Yes, bare Earth point cloud and point cloud.
Okay, so this is basically this part here. So like you can see here, we have the point cloud, and you can see here like we are interested in only looking at the terrain part, and everything which is above the point cloud, is above the ground, whether it's vehicles, individuals, or trees, we filter them. So that's basically, this is what we see here. Oh, sorry, I'm going the wrong direction. So basically, you can see here, you see ground, you see the vehicles, you see the trees, the light poles. This version, you only see the ground surface.
My question is the figure to my right that said all the state RD25
Exactly.
in the top end, because those are the information that you have filtered, and the one in the left is what are the important information. Is that what you're showing?
No, actually, you should look at it the top and bottom. So the top, it's basically the same point cloud, but colored with different schemes. What we have it here is colored by height. Whenever you see blue color, that's low elevation, red is high elevation.
I see. Okay.
What you see here is the same data set, but it's colored by the intensity, because LiDAR gives you the reflectivity of the objects you are looking at. So you can see here you have pavement markers, you have higher reflectivity, so that they appear brighter. You see here those individuals which are wearing the jackets, the retroreflective jackets, so you can see we have more brightness coming from these stripes of the retroreflective material. And at bottom, actually, it's again the same data set, but again colored by height and colored by intensity, but this is only we are looking at the ground elevation data. Did I answer your question?
Yes, thank you.
You're welcome. So another data processing activity that we are also interested in is this semantic and semantic segmentation and classification, or semantic classification of object points or point cloud. Again, we have lots of techniques available for the segmentation, like spatial domain and parameter domain segmentation techniques. They have some problems that, for example, the spatial domain, they are very sensitive to the starting point of the segmentation. The parameter domain segmentation techniques are quite time consuming and computationally expensive. And also semantic segmentation, associating classes with these segmented point clouds, is also quite demanding. So one of the things here that we wanted to develop approaches to do this in a more straightforward, like forward manner, and also we can handle LiDAR data with completely different characteristics that can be applied to airborne as well as ground-based systems. So we developed what we call multi-class simultaneous segmentation approach, which is a region growing, but we do, I would say, more smart choosing of the starting the segmentation process. And also we develop what we call quality control procedures. So it's very naive for us to say that we have a segmentation technique that outperforms all other segmentations. But what we said, that you can have your own segmentation technique, but usually you have some problems in the segmentation, whether it's over segmentation, under segmentation. So what we did is that we developed quality control measures that will fix those problems. So that's some work that we have been working on for quite some time, and the results we get from there are quite reasonable. And then also we can use these deep learning techniques actually to do geometric segmentation and well as also semantic segmentation of the objects. Just because of the time constraints, I'm not going to get into the level of detail, but I will show you actually what we have here. So this is a point cloud data coming from our system. Again, you have these point cloud data colored by intensity, colored by height, and using these deep learning based approaches for semantic segmentation, you can get initial segmentation here of the features you have along your transportation corridor. So that's again a very basic and common data processing activities for the data you collect from your systems. Something else is what I'll hear. So hopefully you are not really distracted by that I'm jumping from different topics, but I would say here that you have data, which is rich data, but you have to really focus on these general application. Intensity normalization. So as we mentioned before, LiDAR actually, it gives you a range between the object and the sensor, as well as gives you information about the reflective properties, because you send a pulse with certain intensity. Some of the energy or this intensity will be reflected back, and how much reflected intensity depends on the reflective properties of the object space. So for example, in transportation corridors, we have the pavement markers, we have glass beads. These are highly reflective markers. We have these signs, they are highly reflective, so we have high intensity. But when you work actually with sensors, like for example, the Velodyne, you have multiple beams. So you have those, in this case, for this sensor, you have 32 beams. And because of the manufacturing process, you cannot expect that each one of those 32 beams, if it hits the same object, it will give you the same intensity. So that's what we have to really normalize these intensity coming from the different sensors, or sorry, different beams on a given sensor. You might have a vehicle with multiple sensors. Again, you would like to normalize the intensity to make sure that the reflectivity coming from the different sensors on board this platform are homogeneous. And you might have even inter-system intensity normalization. You have reflectivity coming from this vehicle here and the reflectivity. And again, in order to integrate data from these two sensors, you have to make sure that the intensity is homogeneous. So that's what we call intra-sensor intensity normalization, inter-sensor and inter-system intensity normalization. So there are different ways actually for doing this stuff. One of them that use calibration. Basically, they do use the system equation, and based on the range and the incidence angle, they evaluate the normalized intensity. But this requires the availability of some targets. You have to have prior knowledge and geometry of the object. So what we are trying to do actually is develop much simpler approaches to allow you to do this normalization, whether it was within the sensor or between the sensors on the same platform or even between systems. So we have this approach here for what we call intra-sensor normalization. And just to give you an idea, this is with one of our vehicles here, we are collecting data. This is a transportation corridor. And usually you have this problems if you are driving on concrete pavement. Because of the sand or the silica in the concrete, you have this very high reflectivity of the road surface here. And sometimes it's a bit hard to see actually the pavement markers from the actual surface. So here, like for most of our application, we are really interested in making sure that these pavement markers are highly visible in the LiDAR data. So by doing this intra-sensor normalization, we take this point cloud and we make actually the intensity values coming from the different laser beams more homogeneous. And to show you the impact of doing so, if you look at that, if you look at the top 5 percentile of the intensity values, which you can say that those most probably should be the pavement markers. These are the most highly reflective markings along the road. So if you use the intensity values as they are, you can see that we have some false positives here, but when you do a normalization, you can see that you have less false positives. You still have some false positives here, but you can see that the pavement markers are clearly defined. And when you work actually with this and multiple sensors on top of the same vehicle, again, if you take actually the point cloud and you do the intra-sensor and inter-sensor normalization, you can see actually that after doing this normalization for the different beams and the different sensors, you can get much cleaner pavement markers here. You still have some noise, but those noise are much easier to get rid of. So this is very important because one of the important applications for this transportation corridor mapping is getting these pavement markers. We need to use these pavement markers to understand the visibility of the pavement markers. That's very important for driving during night, as well as for autonomous and connected vehicles. Autonomous and connected vehicles will rely on the fact that the pavement markers are very visible and they have huge contrast or large contrast from the road surface. So making sure that basically that we have very good ability to derive these pavement markers and evaluate their condition is quite important for connected and autonomous vehicles. So right now we are at the last step where we are doing this inter-system intensity normalization. So regardless of which system you use, we would like to get homogeneous normalized intensity values. So another thing which is related to this is basically the lane marking detection classification. Again, there are lots of work that's being done in this area, but just for the sake of the time, I will jump directly to the work. So we have some approaches which are based on intensity thresholding. So like what we said before, we just say that we take the top 5% and we say those are the lane markers. The other approach is using these deep learning based approaches, but most probably all of you know that the bottleneck in using these deep learning based approaches that you have to have lots of training data, and the labeling of this training data is quite painful. So one of the things we did actually is that we developed actually using this intensity normalization, we can use actually the outcome from the intensity normalization and the detected lane markings, and we use this one to generate the training data. So we have automatically generated label data, and that's one of the key bottlenecks in deep learning approaches, is that how you can effectively and reliably generate sufficient training data for training your network. And then after we get these actually lane marking detected, we actually do some filtering at the end to get these detected lane markings, and then we classify them whether they are edge lines or solid lines, skip lines, or dotted lines. So the next, I would say, data processing activities is trajectory enhancement. And again, if you basically what we have said so far is that most of our applications right now, we rely on the GPS signal. If we have no GPS signal, then we are in trouble because our trajectory will not be of good quality and our point clouds will not be of good quality. So we developed trajectory enhancement techniques using image and LiDAR data. And again, I will just jump to the concept, or to the I would say preliminary, or like the results we have. So this is actually a mobile mapping system, and we mapped an area here under the bridge. So you can imagine that once you get under the bridge, all the GPS signal will be lost, And as a result, actually, if you look at the data before you will have some problems in the trajectory. So this is a cross section of the bridge. You can see that we have alignment issues here on the wall of the bridge. And after trajectory enhancement here, the data becomes much better quality. So what we are doing here is that we use actually the LiDAR data to aid navigation unit to determine better quality trajectory whenever we lose this GNSS signal. So this is just, again, this is before the trajectory enhancement. You can see that the point clouds coming from different times, they are not aligned well, but after the calibration, they align quite well. You have another thing here, this is before and after. So through these actually figures, we are showing that by using LiDAR features, we can improve the quality of the data, and that will allow us to do better interpretation of the data. So again, this is just some examples here. You can see this is the piers of the bridge before the trajectory enhancement, and after trajectory enhancement, you can see lots of improvement here. So the last part of the talk, and I know that I just like to take maybe 5 or 6 minutes here to talk about application-dependent data processing. And that's really the key part here, why all this is important for transportation corridor. So I'll just talk about lane width estimation. So again, this is a figure which I borrowed from a colleague here in transportation. So basically, the lane capacity in terms of vehicles per hours per lane depend on whether the lane width, how much is it, the shoulder width, the percentage of truck. So you can see here that if you have 12 feet lanes, you have 6 feet shoulder and no trucks and no work zone, you can have almost 2,400 vehicles per hour per lane. If you actually have 12 feet lanes in a work zone and 34% truck, your capacity drops from 24,000 vehicles per hour per lane to almost 50%. And in a case like that, when you have 9 feet lane with a working zone and percentage of trucks, your capacity reduced to 1,000 vehicles per hour per lane. So this is just here, this is an example of an actual roadwork. So here you have a compound problem. You have a very narrow lane width, 9.9 feet. Theoretically, actually, according to the design plan, that should have been 11 feet. You have a very narrow shoulder, and you have a barrier, concrete barrier directly next to the shoulder. So as a driver, actually, if you are driving in this very narrow lane with very narrow shoulder and barrier, the stress level of the driver will increase, and as a result, your tendency to slow down, that will be the dominant factor, and you will press the brakes a lot. So that's what makes the vehicle or the lane capacity decrease. So the key is that how you can quickly determine the lane width and convince the contractor that this is really 9.9 feet instead of the 11 feet, which was in the design plan. So this is where we use LiDAR systems. So there are lots of approaches here, but basically what we have done here is that we use this lane marker detections, we develop these lane width estimation, and we provide the DOT with this plot, the mile marker with the lane width. And whenever we have a substandard lane width, we show this to the contractor, and that's basically what I was talking about, the visualization. So we show them where are the pavement markers, and we have these scale bars actually. So scale bar means like red starts from 0 foot to 9, and then yellow, that's 10 feet, 11 feet, 12 feet. So in addition to the plot where we have the mile marker versus the lane width, we show them this visualization. We say, this is exactly where you have a substandard lane width. And from my understanding of transportation, that basically if you have only 20 feet of substandard lane width, that's enough to actually cause congestion on the traffic. And one of the things here that also we are showing here is that by saying actually that by using deep learning networks with automatically generated label, we have much better ability to detect and classify lane markers. So this is ties all the things here. So hopefully you can see that why we are spending time on this system building, the system integration and the calibration and the data processing, because we only after doing that, we can really say that using this point cloud data, we can derive the lane markings and the lane widths. So I'll have maybe just 2 or 3 minutes. So I'll talk about lane marking reflectivity analysis. So again here, just without going too much into details, how is the reflectivity usually done? So this is just a system which is used right now, Road Vista. They have this unit here, which is roughly $100,000. This is some work we did over a couple of weeks ago. So basically you drive, it looks at this lane marker, and at the end gives you standard reflectivity and infrared reflectivity. So for example, here, if you have this edge yellow edge line and this white edge line, you have to mount this unit once on your left to map the yellow, and then you have it mounted on the right to map the edge line. So this is quite expensive, and actually, as I mentioned, this is like $100,000, or basically you have 2 units actually mapping, but actually they have to derive that they have a sort of a very strict tolerance of where the unit relative to the lane marking. So usually you end up by marking or maybe less getting the retroreflectivity for each lane marking at a time. So this is a test we did where basically we used their system, and then this is their retroreflectivity, which is reported by their system. This is the standard and infrared, and this is what we got from LiDAR. And we are able to show actually that the LiDAR intensity data gives you very good data that allows you to get an idea, very good idea about the reflective properties of the data. So just to give you an example, this is the pavement markers, which are extracted from the LiDAR data. You can see here, this is a skip line, and you can see here we have gaps. So if you look at the data, this gaps here is just corresponding to this gap. So again, we show them in the image data and in the LiDAR data and the intensity profile, we have a complete report of the quality of the lane markings. So this is just another example here where basically you can see that, again, the sort of the compatibility of the lane marking reflectivities and the image data as well. So what we have shown actually is that we have an R-square value or sort of correlation value in the range between 60 to 80%. And again, depends on whether how good the lane markings are. So rather than having this standard systems, which basically you drive and map every lane marker at a time, from our system, with one drive run, we can derive reflectivity information for these 3 lane markings at a time. So I think I just want to give more time to questions, so maybe I should stop here, and maybe I'll go to the end slide. So just in conclusion, what we are doing in our area is basically we are taking data and we are trying to abstract this data into information and knowledge. And in order to take this data into knowledge, you have to go through these things here. You have to understand the application needs. And then based on our understanding of the application needs, we take these system design, system development, calibration, we do the acquisition, we do the modeling, and all the way until we derive some information. And then we see, is this information sufficient to make a good decision? And sometimes we have to go back again and restart the whole process. So basically what we have been focusing in my group is on this area here, or this basically pyramid, or this component here of this data to knowledge transformation. So thank you very much for your attention. I hope that this was clear enough, and I have to acknowledge the supporting agencies of our work. And one of the things here that if you see the supporting agency, we have lots of things here related to agriculture. And this is just one of the things here that might be already clear to all of you. There is a very strong link between connected and autonomous vehicles for transportation and for ag. both communities are really interested in having these robust automated systems operating. So, for example, auto steer functionalities was there in the ag domain before actually the transportation domain. So thank you very much for your attention, and I'll be glad to answer any questions.
Thank you so much. It was really great talk, very inspiring. Thank you. So I think we have time for a few questions. Any question? So maybe I will ask one question until we're going to be having more questions coming to the floor. So going back to the lane detection, then you were using LiDAR. Do you have more results to show there on the LiDAR-based lane detection? And what was this, the spec of lane? The reason that I'm saying we have another PhD student here, Michael, who was working a lot on lane detection, but primarily image-based lane detection. So wanted to see how was your insight, and were you able also to make a comparison of image-based and LiDAR-based, if you have any insight into that area?
That's a very important question. So so I mean, we have lots of results. I did not really explain this. So we have, I mean, this is just an example here to give you an idea about this data set. So this data set, hopefully you can see my screen. We draw from Lafayette up to a place here. So we have almost like 130 miles. So this data set we collected in 2 hours, and within 3 days we have this plot. So to derive this intensity data, that's based on our pavement marker detection. And we have done several data sets. So we did survey of Interstate 65 from West Lafayette to Indianapolis, and then from Indianapolis we took 70 all the way. So that's more than 300 miles. Again, we collected this stuff in 1 day. Within 1 week we had the pavement marker. So we have an approach which we claim it's operational, that basically using a sort of different approaches we have, like the intensity thresholding and the deep learning based approaches for processing these LiDAR data. And that depends on several factors like the normalization and also the geometric quality of your LiDAR system calibration. All these make an important impact on the pavement marker inspection. You're actually, what you said, pavement marker detection from the imagery, that's also quite possible, and there is more work in this area. The main problem we see with imagery is that it's first sensitive to the lighting conditions, if you have canopy, shadows, or something like that, as well as occlusion. So basically, especially if you are in Indiana, we have lots of traffic. So if you are on I-65 or on 70, there is lots of traffic. So the problem with imagery, that as you're driving, basically, if you have vehicles next to you or in front of you, you lose all the visual information. The LiDAR data, because you have beams rotating 360 degrees, and for example, in this system here, you have 4 LiDAR units that are emitting close to 3 million pulses per second. They are shooting forward and backward and side. So even if you have at a certain epoch some occlusions, you will have a chance to avoid this occlusion. So with LiDAR, we barely see occlusions because of neighboring traffic. In imagery, that's usually a common problem, in addition to the sensitivity of the images to these lighting conditions.
And do you remember what was the spec of the LiDAR that you were using? I mean, was it a high-end LiDAR or no?
No, this actually is using actually these LiDAR units. Just maybe I will show you the Velodyne. If you have the Velodyne, which is the those are not really high-end units.
Okay.
So just we are using this LiDAR here. This unit is like $3,500.
Yep.
3,000, and then for the vehicle here, so we have this unit here, which is $3,500. This is a little bit more expensive. This is roughly right now $20,000.
I see. And were you using threshold-based the kind of threshold-based techniques when you were using this LiDAR, or no?
Yeah, so we were using, and here, like most of the time, we use this intensity thresholding, but after the normalization. We take care of the normalization first to make sure that the beams are producing the same intensity or homogeneous intensity, and we do this homogenization across the LiDAR units.
And for this particular data set that you were mentioning, were you having kind of synced image and LiDAR data at the same time for kind of sensor fusion for lane detection as well, or
No, I
not?
mean,
That wasn't within the scope.
yeah, we have the data synced together. So because of our work on the system calibration, we have the LiDAR synced with the data, but the lane marking detection is purely based on LiDAR. We only use the imagery to visualize the LiDAR detection. So whenever we have an area that maybe I should yes, so here, like, let me, so the reason we use the imagery, so for example, if you look at this one here, so you can see here, we see the intensity data, we have high intensity data, and then all of a sudden, we have low intensity data. And this is purely based on LiDAR. And what we do actually is that because we have very good geo-referencing of the imagery and data, we say, at this point here, we have that transition from high intensity and low intensity corresponds visually to this. So you can see here that the high intensity, or this one here, is like a new pavement marker, and here you have bad pavement marker. So that's actually where we see the integration of the image and LiDAR data, that we have the LiDAR data gives us the pavement marker very nicely and very robust way, but we use the image data to convey this information, why this is happening, why we have this low intensity to a high to low intensity. And for example, here you see an area that we have weak lane markings. So here we are showing them that really what you have here is that you have worn out lane markings. You can see here that you have very nice lane markings, and we show them that this is really a lane marking. And just to give you an idea, we have some situations where we have the lane markings are very visible in the imagery, but they are not visible in the LiDAR. And we know that this is happening because when they do the painting, they have to apply glass beads to increase the reflectivity at night. So we can tell them actually that even that there is not sufficient glass beads applied during the painting process.
I see. Okay, nice. And then last question, and then leave it for others. May I know if this data set is available publicly or not, the data set that you were mentioning?
We can, I mean, just maybe we can talk offline. I mean, we can make some data sets. There are some data sets which are collected for certain sponsors. Those are the ones we cannot share, but we have some data set which have been collected over campus, and we have a DOI. It's available during through Purdue actually. So you're more than welcome to have this data, and I can share with you the DOI for this data set.
Okay, that's great. Thank you so much.
You're more than welcome.
So, go ahead. Who is asking a question on the chat box? I see some questions. Or anybody else would like to go ahead? Go ahead.
Yes. Thank you, Professor Habib, for the nice presentation. My name is Solomon. I have one question, and the end goal you said is to generate the HD map. And I wonder if you tried and generate one.
Yes, I mean, so like, I mean, generating the high definition maps, again, it depends on what is the information you want to have in the high definition map. So just to say that if you would like to have, let's say, right now we have a very high quality, high fidelity map of the pavement markers. I mean, we did not have a good time, sorry, to show this one. So, and also what we have is that we have the reflectivity. So like the map includes the pavement markers, the reflectivity of the pavement markers, as well as the potholes or surface anomalies, automatically detected along the pavement markers. So all these are reported We have something also like we have ditch line mapping, so we have longitudinal cross-sectional profiles, and we evaluate drainage capability across the one. We are working on the classification of the objects. So all these things, actually, whatever we can extract, that goes directly to the high definition map. But I cannot really tell you that we have a product right now that we give you all this information. Like we presented in a general database, if I understood your question correctly.
Yeah, that's right. Thank you very much. And so my question was then, so we have here the local information in form of the lane width and the lane information and such alike. And at the same time, we do have also global information. And the question that I wanted to ask initially was that how you integrated the two in a way that is easily usable and portable. If there is any encoding scheme that you use. Thank you very much.
So yeah, yeah, like what we do actually is that's mainly in the visualization aspect, and I would like, and this is the part which I did not have a chance to go through this one. So what we do actually is that, again, we are not there in terms of encoding, but what we are really interested in making sure that we can visualize this information here to the user. So this is just to give you an example here of this. So this is basically how we present the data, like visualize the information. So here, if you look at this, we have a visualization environment. We call it iLive, which is Image LiDAR Interactive Visualization Environment. So in this environment, you can see the detected pavement markers. You can see the images. You see the projected pavement markers on the road. You can see like this is like cyan. That basically says these are the physical lane marking. The those magenta, that's like the interpolated lane marker. And you have the scale bar. Basically, this is where the operator can know actually that, for example, in this case here, the lane marker, the lane width is close to 12 feet. So this is the environment where we are showing all the results of our processing. And for example, if we have utility poles, they are also represented in the 2D imagery as well as in the 3D point cloud. Did I answer your question?
Yeah, sure. Thank you. Yeah. For further information, I will reach out to you. Thank you very much.
Yeah. So just one quick comment here related to the previous question about the image-based pavement marker condition. So again, you can see here, this is one of our data collections on, I think this is I-70 or I-65, I don't remember. So you can see here we are driving east into the sun. So you can see the quality of the images here will make it very hard to have this robust detection of the lane marker. However, using the LiDAR data, because it's an active sensor, at the same time, we can easily see those pavement markers.
Yeah, along the same question, how do you measure the depth of a crack on the road? What are the kind of sensor that you use?
Okay, so this is actually, and again, I have to really apologize for missing this part, but which I had to skip.
No, my question was about the depth of a crack. What kind of?
Yeah, that's what I'm trying to say. So in this case, actually, if we really would like, I mean, you remember we mentioned that we have two systems. One of them is the based on the transit system, and this is based on the F-150. So here we have these sensors here. Their accuracy is in the range of 2 to 5 millimeters. So basically, the way we detect the cracks or the potholes, that basically if you have the LiDAR system scanning a homogeneous surface or like a planar surface, it behaves in a nicely in basically in this straight line. Whenever you have a crack, you change the beam the shape of the beam will change. So we do this first to detect the presence of anomaly on the road surface, and then we determine based on that we can derive from the LiDAR a very accurate estimate of the anomaly. So you can see here, this is just some dirt here. This is like they had this patching process. You have some of these actually cement remaining. That's basically, this is the anomaly here. So we can very accurately derive an accurate information about the height of this object. So just to give you an idea, and this is, again, I apologize that missing this one. We believe actually that, and this is what we did this stuff for fault detection, for runway inspection, and we believe that reliably anything which is more than 2 centimeters or like slightly less than 1 inch, we can derive its information directly, but you have to have this high-end unit, not really the other unit, which was an accuracy of 1 inch to 2 inch level. Hopefully I answered the question.
No, but my specific question is, okay, I know you can detect the crack, but what is more to me is what is more important is what is the depth of the crack? How do you measure the depth information?
Okay, so maybe I was not clear. I apologize for that. This is a 3D point cloud. So this point cloud is XYZ.
Yeah.
So every feature here has an XYZ. So basically we know the distance between this point here and this point here, and that's exactly the depth of the crack.
Yeah, but this is like some crack. It may visually we may not be able to see it, but it is there.
But I mean, what do you mean? You cannot see it? You mean it's like you're talking about a crack which is
the crack
less than a millimeter or something like that?
Remember that we see some anomaly. Okay, then beneath that it's a crack with maybe 1 inch or 2 inch depth. So we know that this is really serious.
Yeah, if the crack is visible, and because the LiDAR is just basically whatever we can see in the LiDAR, we can, like, if there is a crack and basically we have LiDAR reporting some information along the crack, we can measure the depth.
Okay.
Maybe I misunderstood the question.
That's fine. Okay, so with LiDAR, you're able to measure the depth. That's what.
Yes, you can measure the depths, but you have to make sure that, like, because LiDAR is a line of sight. So as long as the laser beam hits this points along the crack, definitely you can see it. So we can, like, really see if we have these joints, we can model them and we can see them. Again, if you really want to have higher level of detail, you have to make sure that you drive a little bit slower, and then you will give the LiDAR more opportunity to see those cracks here.
Okay, thank you.
You're welcome.
Okay.
Okay, I think it's already 4:15, and I see that there has been some other question in the chat box, and might be some other questions that still you may want to ask. So let's. I don't think that we have time for any further questions. Dr. Marifa, do we have time for one more question?
Yeah, but let me make an announcement before everybody else leaves. Okay, next week we're gonna have Professor Dipankar Das Gupta from University of Memphis. His talk is about use of AI technique in cyber security. One more, yeah. Just this is the last question.
Okay, great. Okay, so let's go for one last question, if any. So I see a bunch of questions in the chat box. So if you would like to ask one more question that we do have. Anybody wants to ask a question? Okay, so everybody is shy. I think I can read one of the questions in the chat box. The question is that you already mentioned about one condition that LiDAR data cannot detect the lanes or some other. So would you also make some other comments on the situations that LiDAR is performing poorly compared to image, if there are some situations?
I think I mentioned that in some cases the image, I think maybe I misspoke. No, LiDAR, in terms of the ability of LiDAR to see the lanes, is much better than imagery. Because LiDAR, because you have this spinning multi-beam laser units, so basically it's not really occlude, like it's not really sensitive to occlusions or neighboring traffic as imagery. Also LiDAR, because it's an active system, it's not really impacted by the lighting conditions. So if you're driving into the sun, LiDAR will still operate. Imagery will be sensitive. So these are the I would say the advantages of LiDAR over imagery. The other way around, like the advantages of imagery over LiDAR, and I'm not sure if this is, you can really say that this is the case, but if you have a pavement marker that basically there is no enough retroreflective material applied to it, the LiDAR will not see it. However, the image will see it. But the question is that something good or bad? I mean, because usually you would like to make sure whether you can, whether these retroreflective glass beads have been applied to the paint or not.
Okay, I think great. Okay, thank you so much. I think it is now 4:20 Friday afternoon. Thank you so much, Dr. Habib, for today's talk, and also for all you that attended today's talk. And wish everybody a great weekend. Thank you so much.
Thank you
very much.
Thank you. Bye-bye.
Thank you. Bye.
Bye.